So, in this lab, we're talking about um, pH indicators and looking at what type of indicator would best fit a certain acid base titration. So, when you're titrating an acid and a base, it could be a weak acid with a weak base, or a strong acid, strong base, or a weak acid with a strong base, or a strong acid with a weak base, and so on. All right. So, when you do these acid base titrations and you neutralize the acid and the base, the end point when they are neutralized could either be neutral, like around pH 7, or it could be in the acidic region below 7, or in the basic region above 7. All right. So, in order um, to to be sure that you have reached the end point, you need what is called as an indicator. So the indicator is an organic dye, and in most cases, an indicator is either a weak acid themselves or a weak base. And so what happens is, because it's a weak acid, now for example, if I use the general formula for an indicator as HIN, where the H part is that proton, all right. So in this case, the HIN indicates that the indicator is a weak acid. So the H is the proton that, when the indicator dissolves in water, is stripped off, and then it forms the conjugate base In minus. All right. Okay. So since it's a weak acid, most of the time the form it exists in solution is the undissociated, or the acid form. All right. A little bit of the conjugate base will form, but not as much as the acid which is undissociated. All right. So this undissociated acid will have a certain color, and the conjugate base will have a different color. All right. So in case the resultant solution from an acid base titration is acidic, all right, then it would have the color of the undissociated indicator. All right. And if that acid base neutralization is basic, uh, the the endpoint is in the basic region above 7, then it would probably be the indicator which is in the form of the conjugate base, since that has a different color. All right. So this color change between this undissociated and the dissociated part, the conjugate part of the indicator, it happens in a very narrow pH range. All right. So it happens in a very small range of pH conditions. And this is then called the pH range for that given indicator. Okay. So, for example, you have a strong acid like HCl and a strong base like NaOH in a neutralization reaction, and the resultant solution is going to be neutral, pH 7. All right. So to start with, it's going to be acidic because all you have is HCl in the flask, and then in the burette you have the NaOH, which you're going to be adding 1 drop at a time. All right. So if you use an indicator like phenolphthalein, it's going to be colorless because phenolphthalein is colorless below pH 7. All right. So initially, when it's just acid, it's going to be colorless. So as you gradually add the base, the pH is going to slowly rise. All right. And once you hit that pH 7 and reach neutralization, one little bit more of the base would make the pH a little bit basic, little alkaline, say around 8. All right. So when the pH reaches above 7 in basic condition, the phenolphthalein then turns like a magenta or a pink color, all right? So the range for phenolphthalein is between 5 and 8, okay? So at 5, it would be still colorless. You'll see a slight pink developing gradually, and by the time you hit pH 7, which is where the end point is, and a little above that, pH 8, it becomes like this light pink color, all right? So you can definitely tell that the acid has been neutralized by the base because of that color change that happens, okay, from colorless to pink. So between 5 and 8 is the pH range, and that incorporates the endpoint pH, all right? So therefore, phenolphthalein would be a good indicator for a strong acid, strong base titration. Okay, so these are some examples of indicators, and let's look at their ranges according to the color changes, all right? So I used colors here so as to mimic the conditions of what the color change would look like, all right? Now, if I use either universal or cabbage solution, I'm able to do all kinds of acid-base titration. So, for example, universal, between pH 1 and 3, there is a very distinct, a sharp color change from red to yellow, all right? So therefore, if I'm doing an acid-base titration that falls in a very high acidic pH range, all right, where the endpoint is in a very high acidic pH range, so it's in this low pH range, I could use universal, or I could even use cabbage, because cabbage is going from red to like light purple. And then if I have a different pH range, I can still use universal or cabbage, because again, you see between 6 and 9, you're going from yellow to green. And then again, at a higher basic pH range, I can still use universal because it goes from green to blue. Okay. Same thing with the cabbage. So I'm able, with cabbage and universal, you're able to use this in various types of acid-base neutralization, whether it's a strong acid, strong base, or it's weak acid, weak base, or weak acid, strong base, and so on, all right? Because they have so many different distinct color changes at different pH ranges, okay? Now, next, if we look at the blue litmus, you can see that it has one single distinct color change. And if you're going from pH 5 to pH 7 or pH 8, all right? So between this 5 and 8, you can see that it has a color change where the red is gradually disappearing and then blue appears, all right? Okay, so if I'm using an acid-base titration whose endpoint is either pH between pH 6 and 7, then I can definitely use a blue litmus. Now, red litmus also has a single color change, and that's between 6 and 8 or 5 and 8, okay, kind of like the blue litmus. And again, the distinct color change is from red to blue. Phenolphthalein, if I look, the distinct color change would be from colorless, all right, where it's gradually getting pink. So like between 6 and 8, and a little over, about 9ish, it gets a deeper pink, all right? So you have a wider range. It's more in the basic area where you're seeing the color change, okay? And then you look, thymol blue, it goes from yellow to blue. The range would be between 6 and 9, all right, or a little bit higher, 8 and 9 rather. If you look at pH 8 it's yellow, and then in pH 9 it becomes blue. So maybe say 7 to 9. All right, so that would be a good range for thymol blue. Phenol red, again yellow to red. Okay, again a very distinct color change. So between again 7 to 9, all right, would be its range. Bromothymol blue, you can see it goes from yellow to blue. All right, so this is kind of between 6 and 8. All right, so 6 and 8, it has that distinct color change from yellow to blue. All right, and then methyl red, it's going from pink, so it's more in the acid region. All right, so you're going from pink to yellow. All right, it's still in the acid region, so 4 and 7. All right, or 4 and 6 rather. All right, so methyl red would be good for a neutralization where the pH is kind of between 4 and 6. All right, the endpoint is between 4 and 6. All right, so for a more acidic condition. Okay, bromothymol would be good for acidic condition as well as basic conditions as well. Okay, phenolphthalein would have to be more in the neutral region. Okay, Cabbage and Universal, you can use it for any type of neutralizations, all right, whether it's an acidic or neutral or basic. So you need to get a sharp, visible color change at the neutralization point. That's how you choose your indicator. For if it's a strong acid and a strong base titration, you have to use an indicator which shows the sharp color change in the more basic region, all right, in the higher pH region, which is why for the HCl NaOH, phenolphthalein is the ideal indicator, because there's a sharp change from colorless in the acid region to pink in the basic region. Okay, for a weak acid strong base, you use an indicator whose color change is more in the acid region. All right, okay, so it's in the lower pH region, not in the higher pH region as in strong acid strong base. All right, so for example, if acetic acid and sodium hydroxide are getting reacted, then you're going to use methyl red, because if we go back, methyl red goes from pink to yellow. All right, and that's in the acid region. All right, so methyl red is good because it goes from pink to yellow in the lower pH range. For a strong acid and a weak base, you're going to use an indicator which shows a color change in the basic region, the higher pH region. All right, so for HCl ammonia, you're going to use bromothymol blue, because again, if you go back, bromothymol blue goes from yellow to blue around, and the range is between 6.2 to 7.6. All right, between 6 and 8, basically between 6 and 8. Okay, so more in the basic region because it's above 7. Okay, the range is above 7, a little below 7 and above 7. Okay, all right. So the first experiment starts with taking 0.1 molar HCl solution in a test tube, 5 ml of it, and then adding 5 ml of water, so a total volume of 10 ml. All right, so that first test tube 1, the concentration of the HCl is going to be 0.05. Okay, so since it's a strong acid, when it ionizes, its H3O plus would be equivalent to the acid concentration. So this test tube has 0.05 molar H3O plus. Okay, then you take the negative log of this and you get the pH, the corresponding pH. Right, we'll stop here and continue this in the next slide.